Now, what we've done so far is we've been playing around with triple integrals, and we've discovered that sometimes we have a lot of difficulty in trying to evaluate an integral just in rectangular coordinates. So we've looked at cylindrical coordinates. Well, now we're going to proceed and look at the next coordinate system that we're going to use in triple integrals, and that being spherical coordinates. Now, before we actually use spherical coordinates to set up an integral, a triple integral, we need to go back and review a little bit what the spherical some basics about the spherical coordinate system. Now, remember, spherical coordinates consist of the rho, the theta, and the phi. And I want to real quickly just remind you what those are. First of all, the theta is the angle on the xy plane, and it's just what we think of, it's the same old theta. You have a terminal side and an initial side and a terminal side, and the angle made there is the theta. So it's on the xy plane. So that's nothing new there. Now, this new angle here, phi is the angle that's made with the z-axis, as you can see here. Okay, so if the z-axis is the initial side, and then you rotate and you get a terminal side. So it's the angle made with the z-axis. Rho is the distance from the origin up to the point. So it's like, you can think of it as the radius of a sphere. Now, here's what we need to do. We need to remember some things. When we're converting, remember that x is equal to rho sine phi times cosine theta. That's what x is. Y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. So we want to remember that, and of course, remember also x squared plus y squared plus z squared is equal to rho squared. So these are just some basic facts that we need, and we're going to use those because what we're going to do is we're going to take a function that's in terms of x, y, and z, and we want to write it in terms of our spherical coordinates. So this would be like rho sine phi cosine theta. And I guess this is a little redundant, but just to show you how this looks. There, like that. Okay, now, let's go ahead now. I think that's enough information to go ahead and start defining one other thing. One other thing I want to point out. Another one of these identities that we found was that r squared is equal to rho squared times sine squared phi, like that. So that's another one of the properties that if we're going from, for example, from cylindrical to spherical, this is one of the properties that we had. So now I think we've got it. Okay, now, in defining or in setting up these triple integrals, we need to just remember that we approach this the same way we always have. We play this game where we take a region under a solid, a region under a surface, the solid region, and we divide it up into these sectors. A polar sector, a cylindrical sector. Here I'll call this a spherical sector. And we divide it up into those little parts. We let there be infinitely many of them. They're going to be infinitely small, and we add them up. That's what our integral does. It adds up all these little things, all these little spherical sectors, and we say, okay, that equals, for example, the volume, if we're thinking in terms of volume. But here I've got a picture here, and I didn't know if this picture would be clear enough, so I've got a couple of things we can look at. But here you can see the spherical sector right here. And here it is off to the side. And I just cut this and pasted it out of the OpenStax book. Okay, so there's what we have. And I have another picture down here that might help us also. Here I've got just an XYZ axis, and you can see the little spherical sector. And I've got it blown up over here. Now, recall this, that when you want the arc length of a circle, if you want to find the arc length of a circle, what you can do is this. You can just say, well, the arc length is equal to theta times the radius. So for example, let's suppose you have a circle that has a radius of 4. And you want to know what is the arc length around the entirety of the circle. Well, there are 2 pi radians in that circle, and the radius is 4, so you get an arc length of 8 pi. So that's the circumference. Well, that principle applies no matter where you are on the circle. Let's suppose that you don't go around the full circle. Let's suppose you go around a quarter of it, so that theta is pi over 2. And you want to know that arc length. Well, that arc length is going to be 2 pi because it's 1/4 of 8 pi. But here's the way it would go. It would go pi over 2 times 4, which would be 2 pi. 2 pi. So that would be the arc length. Okay, so we want to keep that in mind here, because what we need to do is we need to think about what's going on with this sector, because what I want to do is approximate the volume of this sector. Now, if you think about on the x-axis, and think about this arc length right here. So if you think about, this is the theta part. So we've got an angle going up here. This is like the theta. And I could say, well, that's d theta. So I could say, okay, this angle here is delta theta. And I want to talk about, well, what approximately is that arc length there? Well, that arc length is going to be delta theta times r. Okay, so that's what that's going to be. Now, we want to use the same reasoning for this length here. But now the angle that we're considering is not theta, it's going to be phi. So if we want to talk about the arc length there, it's going to be rho times delta phi. Okay, now let's look at something else here. We still need to figure out, well, what is this length here? Well, this would be delta rho, because here's where one row ends and here's where another one ends. So this is the delta rho here. Now, if we wanted to calculate the volume of this thing, we could do this. We could say, well, I'm going to take delta theta r, and then times rho delta phi times delta rho. And we could say, okay, this kind of looks like a way that we could get an idea about the volume of that thing. But here's part of the problem. We've got an r in here. And the r really doesn't belong in spherical coordinates. So let's see what we can do with that. Remember that we have this situation. We know that r squared is equal to rho squared, rho squared times sine squared. We know that to be the case. Now, if that's the case, we know this also. Now remember, phi goes between 0 and pi. So sine of phi is always positive, and rho is always positive. Therefore, I can take the square root. I can say, well, that equals rho sine phi. Now, if that is rho sine phi, that means that delta theta times r can be written this way. Rho sine phi delta theta. So now, let's see what we have now. If we put all of this together, what we're going to get is we're going to get rho sine phi And then what else do we have? Let's see. Okay, so we've got this one. Okay, we've got this one. Now I've got rho, delta phi, and delta rho. Rho, delta phi, delta rho. Okay, so here we go. Rho, delta phi, delta rho. Now, if we kind of put that together, look what you get. You get rho squared sine phi delta rho, delta phi, and delta theta. Did I leave off the theta? Let's see. Did I leave off? I forgot the theta on here. Let me just put it here, delta theta. I forgot it. Okay, it's up here. Okay, it's delta theta. So there we have it. Now, this is what's going to be just sort of the basics of our integrand. We can put another function in there, but this is what's going to be just the basics. So what we're going to have is we're going to have an integral that looks something like this. We're going to integrate over some region, and what's going to go in here is rho squared sine phi d rho d phi d theta. And we don't have to go in that order. It doesn't have to be d rho, d phi, d theta. We could change the order. But this is what we're going to use. Now, let's look at it. Okay. Let's suppose that we want to calculate the volume that's indicated here. In other words, what I want, I have a cone, and that cone is modeled by this expression. And then I have a sphere, x squared plus y squared plus z squared equals 9. And what I want to do is I want to calculate the volume that's bounded above by the sphere and below by the cone. Well, this is just a perfect setup for spherical coordinates. The giveaway is, the hint is that we have sphere, right? We're dealing with a sphere. So oftentimes that's when we're going to use spherical coordinates. So here I go. I'm going to set up my integral. And first thing I do is I put rho squared sine phi. And then I've got to determine how to go about my integration. I think what I'll do first is I'll integrate with respect to rho, then phi, and then theta. Now, first of all, rho. Rho is simply going to go from 0 to 3. I mean, no matter what, there's nothing to keep it from going from 0 to 3. So we're just going to have rho goes from 0 to 3. Now, next, I want to jump over here and put what theta is. You can see that if you just look down on the xy plane, theta is going to go from 0 to 2 pi, like that. Now, the question is, well, what does phi do? Well, that's what we got to figure out. In other words, what we've got to do is we've got to look at this and see what this angle is right here. Now, since you realize it's a cone of this form right here, you know that it's going to be pi over 4. We're going to go from 0 to pi over 4. But let's see how we can know that. We know that z squared equals x squared plus y squared. Okay? Since I know that, I'm going to put that in here. Okay, so I'm going to put in place of x squared plus y squared, I'm going to put z squared. So now I have z squared plus z squared equals 9. And what I'm doing is I'm finding where these two curves intersect. I'm finding the z value where this surface here of the cone intersects the surface of the sphere. So what I get then is I get 2z squared equals 9, or z is equal to 3 over the square root of 2. Okay, now, so you might be wondering, well, how does this help us? Because we need an angle. Well, now remember this. Z is equal to rho times cosine of phi. Now, we know a couple of things here. We know that z is 3 over the square root of 2. And we know rho is 3. This is something that we can solve. Okay? So if we put our minds to it, we can say, well, cosine phi is equal to 1 over the square root of 2, or you might be familiar with the square root of 2 over 2, and of course that corresponds to pi over 4. So what we would do then is our last step would be to put 0 to pi over 4. Now, after we get that part done, then it's just a matter of integrating this as usual. And we're integrating with respect to rho first. So what's going to happen is you're going to have 1/3 rho cubed. Rho goes from 0 to 3, and you would proceed that way. So at this point, everything's the same as we're used to.